In 1984, astronomers photographed for the first time a planetary formation disk around another star. The system was called Beta Pictoris. From that day forward, it became astronomy's laboratory, the most observed, most studied, most analyzed place in the history of the discipline. Thousands of researchers, dozens of instruments, hundreds of published papers. Comets were discovered there, planets, asymmetries, complex structures. We thought we had seen everything it had to offer. In July 2026, James Webb was studying a planet this system has been known to host since 2008, when a signal appeared where nobody was looking. Not a bright blob in an image, a chemical fingerprint, a molecular barcode, the absorption lines of carbon monoxide, in a region where the model predicted nothing but dust. The lead researcher said the exact sentence nobody expected. We weren't looking for a new planet. That signal was a giant planet, at least twice the mass of Jupiter, hidden for 40 years in the bright disk of the most studied system in astronomy. Not because it was small, not because it was faint, but because every instrument used until now to search for planets in this system was blind to this type of signal in this type of environment. Beta Pictoris d is the first planet ever directly characterized in space that was discovered primarily through its atmosphere, through its chemistry, not its light. And that distinction changes something fundamental in how we understand what we know and what we have missed. In this video, we are going to see what Beta Pictoris really is and why it became astronomy's unique laboratory over 40 years. We are going to see the two planets we thought we knew and why we believed we were close to a complete picture of the system. We are going to see why the debris disk concealed a giant planet for so long and how James Webb bypassed that fog through chemistry rather than light. We are going to see what the presence of a third giant changes for our understanding of planetary formation. And we are going to see what this new detection method implies for everything we thought we knew about neighboring planetary systems. Stay through the end, because the question this discovery raises, how many giant planets are still hiding in systems we believed were fully mapped, does not yet have an answer. Astronomy's laboratory, there are places in the universe we have observed so extensively for so long, with so many different instruments that we come to believe we know them. We have mapped every detail. We have modeled every structure. We have tested the predictions, and the predictions prove correct. There are no surprises left to expect, only confirmation, additional precision, more decimal places. That certainty is one of the most comfortable mistakes science can make. 63 light-years from Earth, in the constellation Pictor, lies the star Beta Pictoris. For astrophysicists around the world, it is not simply one star among the hundreds of billions contained in the Milky Way. Something far more valuable, a laboratory. For more than 40 years, Beta Pictoris has been the most observed, most studied, most analyzed planetary system in formation in the history of astronomy. Thousands of researchers, dozens of ground-based and space instruments, hundreds of published scientific papers. We thought we knew this system the way you know your own home. On July 15, 2026, NASA announced that James Webb had just found a giant planet there that everyone had missed for 40 years. The story of Beta Pictoris begins in 1983. The IRIS satellite, the infrared astronomical satellite, the first infrared space telescope in history, was conducting a systematic survey of the sky. Examining the data, astronomers noticed something unusual around this relatively nearby star, an excess of infrared radiation far more intense than the star alone could produce. That could only mean one thing, or matter orbiting it. Dust. A lot of dust. The following year, in 1984, Bradford Smith and Richard Terrell aimed a ground-based telescope equipped with a coronagraph, a device that masks the light from the central star toward Beta Pictoris. What they saw stopped them cold. A flattened, enormous debris disk stretched out on both sides of the star across hundreds of billions of kilometers. For the first time in the history of astronomy, a human being was looking directly at a circumstellar disk around another star. Not an inference. Not a model. An image. This was a founding discovery. Since the 1750s, the nebular hypothesis of Kant and Laplace had proposed that planets form from rotating disks of gas and dust around young stars. In 1984, we saw that disk for the first time. Beta Pictoris instantly became one of the most important astronomical objects in the sky. And it would never stop delivering surprises. Through the 1990s, repeated observations revealed irregularities in the disk asymmetries, warps, a slight tilt between the inner and outer planes of the disk. These anomalies were not random. They were the traces of gravity pulling from inside the disk, the signature of unseen planets sculpting the material around them. We could not yet see them, but we knew they were there. In 2003, another astonishing observation. Astronomers detected variations in the light of Beta Pictoris corresponding to comets plunging toward the star. These objects, called FEBs, falling evaporating bodies, confirmed that the system contains reservoirs of small icy bodies similar to our own Kuiper belt that vaporize when they pass too close to the star. Beta Pictoris was not a static disk. It was an active system, in motion, under construction. In 2007, Hubble observed the vertical structure of the disk in detail and concluded that Pluto-sized bodies' planetary embryos were undergoing runaway growth into even more massive objects. The system was finishing its planetary construction in real time, before our eyes. It is so close, so well oriented toward us, its disk is seen almost perfectly edge-on, perfectly flat in our field of view, and so bright that it became the textbook case of planetary formation. Then came 2008, and everything changed. What Beta Pictoris really is, before telling what happened next, it is worth understanding what Beta Pictoris actually is. Not just what it hosts, but what it is, and why that nature makes it unique among nearby stars. Beta Pictoris is a young star. Very young. Its estimated age is about 23 million years. To put that in context, the Sun is 4.6 billion years old. Our solar system formed 4.5 billion years ago. The dinosaurs went extinct 66 million years ago. At 23 million years old, Beta Pictoris did not yet exist when the last dinosaurs walked the Earth. 23 million years on a cosmic scale is an infant. The star has barely emerged from its formation phase. It has only just switched on triggered the nuclear fusion reactions in its core that will keep it stable for billions more years. Around it, the disk of gas and dust that gave birth to its planets is still there, still massive, still luminous, still slowly dispersing. The planets are young too. They have not finished taking their final shape. Some are still growing by swallowing planetesimals and comets. That is precisely why Beta Pictoris is a laboratory. When we observe our own solar system, we see the finished result, 4.5 billion years of completed processes, erased traces, past history. We cannot travel back in time to see how the planets formed, how they migrated, how the primordial disk dispersed. Everything we know about the formation of our own planetary system has been inferred backward from the final state. Like a detective arriving at a crime scene billions of years after the fact, Beta Pictoris is the crime scene live. A system so young that planetary formation is not finished, that traces have not been erased, that processes are still active and visible. Observing Beta Pictoris is observing what our own solar system may have looked like 4.5 billion years ago. The star itself is of spectral type A6b, hotter, more massive, and more luminous than the Sun, with roughly 1.75 times its mass and about 9 times its luminosity. It radiates blue-white, the characteristic glow of young massive stars. It sits in a region of the sky astrophysicists call the Beta Pictoris moving group, a cluster of stars born at roughly the same time, from the same giant molecular cloud, in roughly the same region of the galaxy. These stars share the same age, the same basic chemical composition, the same primitive history. Beta Pictoris is the brightest and most observable star in that group, making it the ideal representative of what are called nearby young stars. The debris disk surrounding it spans hundreds of billions of kilometers. It is made of fine dust silicate and carbon grains and larger bodies, planetesimals ranging from a few kilometers to a few hundred kilometers across, the equivalent of the asteroids and comets in our own solar system. This disk is divided into two planes slightly tilted with respect to each other. We have known since the 2000s that this tilt is caused by the gravity of orbiting planets, the same phenomenon that creates Saturn's rings or keeps our own asteroid belt in place. The disk is a living, dynamic object, structured from the inside by gravitational forces invisible to the eye. And it is that exceptional visibility of the disk, bright, close, seen edge on that made Beta Pictoris so valuable. And paradoxically, it is also what hid the planet the longest. The two planets we thought we knew in 2008, a team from the Paris Observatory led by Anne-Marie Lagrange accomplished something nobody had managed before in this context. They directly photographed a planet in orbit within a debris disk. The planet was named Beta Pictoris b. This discovery was historic on multiple counts. Beta Pictoris b is one of the first exoplanets ever directly imaged and the first identified in an active planetary formation system. Seeing a planet in a planetary formation disk orbiting its star, it was exactly what Kant and Laplace had imagined 250 years earlier, made visible for the first time. Beta Pictoris b is a colossal planet. Its estimated mass is roughly 9 to 13 times the mass of Jupiter, so massive it flirts with the boundary that separates planets from brown dwarfs, those failed stars that never managed to ignite nuclear fusion. It orbits between about 8 and 15 astronomical units from its star, farther than Mars, closer than Saturn, on a trajectory that takes roughly 22 years to complete. As it passed closest to the star, around 2017, astronomers were able to directly measure its speed across the sky, confirm its orbit, and refine its mass. What makes Beta Pictoris b particularly compelling is that you can watch it move. Over a few years of observation, from one side of the star to the other, it completes a visible portion of its orbit. It actually moves in our images. That is an immediately graspable reality. That point of light in the disk is a planet, and it is orbiting. Astronomers followed it for years. They measured its gravitational effect on the disk. The warps it causes in a disk structure matched exactly what the models predicted. It is real, measurable, predictable. For 10 years after its discovery, Beta Pictoris b was the only known planet in the system. Researchers thought the system might contain just one large planet, with the rest being disk. Then came 2019. That year, the gravity instrument, installed at ESO's Very Large Telescope in Chile, detected a second planet. Not by direct imaging this time, but by radial velocity, the method that measures the wobble of a star caused by the gravity of an orbiting planet. The planet was named Beta Pictoris c. Beta Pictoris c is different from b. Closer to the star about 2.7 astronomical units, in the inner region of the system, far hotter. Lighter 2, roughly 8 to 9 times the mass of Jupiter. Its orbital period is only about 3.3 years. And it is far harder to observe directly, because it is drowned in the intense light of the central star. With these two known planets, the Beta Pictoris system appeared complete, or at least sufficiently explained. Beta Pictoris b, massive and distant, sculpts the outer disk. Beta Pictoris c, closer in, helps maintain the inner structure. Dynamic models correctly reproduce the disk asymmetries observed over 40 years. Everything fit. Everything was coherent. Everything was wrong. The fog that hid everything to understand why a giant planet could remain invisible for 40 years in astronomy's most scrutinized system. You have to understand how direct imaging of exoplanets works and why Beta Pictoris's debris disk is at once its greatest asset and its greatest obstacle. Directly imaging a planet orbiting another star is one of the most difficult challenges in modern astronomy. The problem is straightforward to state. A star is millions to billions of times more luminous than the planets around it. Trying to photograph a planet next to its star is like trying to photograph a firefly resting on the shade of a lighthouse from several kilometers away in broad daylight. The lighthouse's light completely drowns out the firefly. To work around this, astronomers use coronagraphs masks that block the light of the central star, allowing what surrounds it to become visible. This is the technique that allowed Beta Pictoris b to be photographed in 2008. But the technique has limits. It works well for planets far enough from their star that the light contrast allows the planet's signal to emerge from the background. For planets that are close in or embedded in cluttered environments, it fails. And Beta Pictoris's disk is exactly that kind of cluttered environment. The debris disk is luminous, immensely luminous, compared to a planet. It scatters the star's light in all directions. When an instrument points at the system, it does not see a black background dotted with discrete points. It sees a bright, noisy, structured background in which weak signals are lost. It is like trying to read a map in luminous fog. The text may be there, but the background noise is so strong that you cannot make it out. Beta Pictoris d orbits about 30 astronomical units from its star, a distance comparable to Neptune's orbit in our own solar system. It is the farthest out of the 3 known planets in the system, but even at that distance, it remains inside the inner edge of the debris disk. It is immersed in the fog. For 40 years, every time an instrument looked into that region of the system, it saw disk, bright dust, scattering structures. Never an isolated point of light that could be identified with certainty as a planet distinct from the background. Perhaps Beta Pictoris d's signal was there, in the data, for years buried in the disk's brightness, confused with instrumental artifacts or complex scattering structures, rightly dismissed as an unidentifiable source. There was also a problem of expectation. The dynamic models of the system, built on the data from B and C, did not formally predict a third planet in this region. The disk's asymmetries seem to be explained by the 2 known planets. Why actively search for something the model does not call for? In science, you often only find what you are looking for. And nobody was actively searching for a third giant planet in the inner disk region of Beta Pictoris because nothing in the existing models seemed to require one. There is also a technical paradox worth naming that worked against detection. The closer and more favorably oriented a system is, and Beta Pictoris is exceptional on both counts, the brighter and more extended its debris disk appears in our images. It is a curse of observational success. The systems we choose to study intensively because they are close and favorably inclined are precisely the ones where the debris disk is most problematic for direct imaging. Beta Pictoris, oriented almost exactly edge-on, presents its disk in its full luminous extent. That is what makes it such a rich object to study. It is also what makes it one of the most difficult environments for searching for planets by direct imaging. The next hidden planet in a forming system will probably be found in the same type of environment and will be equally invisible to the same techniques. Until James Webb looked by accident. The night James Webb read an atmosphere, Aidan Gibbs is a postdoctoral researcher at the University of California, San Diego. In 2006, his team was using James Webb to do something very precise and very bounded. Observe the atmosphere of Beta Pictoris b. Not search for new planets. Not map the disk. Study a planet already known since 2008. Its atmospheric molecules, its temperature, its chemical composition. For this observation, the team used James Webb's NIRSPEC instrument, the Near-Infrared Spectrograph. More specifically, NIRSPEC's IFU mode. The integral field unit. This mode is unusual. It does not produce just an image. It does not produce just a spectrum. It produces both simultaneously for every pixel of the image. Understanding what that means takes a moment. A spectrum is the decomposition of an object's light into its constituent wavelengths like a prism splitting white light into a rainbow. Each molecule, each atom, absorbs or emits light at very specific wavelengths, unique to it like a fingerprint. Carbon dioxide absorbs at certain wavelengths, water at others, methane at others still. Carbon monoxide produces a series of highly characteristic absorption lines in the infrared, spaced like the teeth of a comb, instantly recognizable. When NIRSpec in IFU mode looks at the Beta Pictoris system, it does not simply photograph what it sees. It analyzes the light from every pixel in the field of view, simultaneously. For each small patch of the image, it measures the full spectrum. This is an extraordinary information-gathering capability, hundreds of simultaneous spectra, spanning a broad wavelength range with James Webb's infrared sensitivity. Gibbs's team analyzed the data. They were looking at Beta Pictoris b, where it was supposed to be, to the left of the star. The spectrum of B appeared as expected, the molecular signatures of a young gas giant atmosphere. Everything matched previous observations. No surprises. Then, someone looked at the rest of the field. And in the region to the right of the star where there should have been nothing but disk, nothing but dust-scattering starlight, something appeared. An unexpected signal. A source of light that had no business being there. The initial reaction was not excitement. It was suspicion. Jean-Baptiste Ruffiot, a research scientist at UK San Diego and principal investigator of the first Webb observations in this program, put it plainly, we've learned not to trust bright blobs in images. They can be instrumental artifacts or other structures in the debris disk. A blob in an image proves nothing. Instruments produce artifacts. Debris disks produce complex structures. Identifying a bright blob as a planet would be naive. What you want is to understand what that blob is saying, and that is where NIRSpec's IFU mode changed everything. Because the blob was not just a blob, it had a spectrum. And examining that spectrum, the team saw something immediately recognizable. A series of regularly spaced dips corresponding exactly to the absorption lines of carbon monoxide. The barcode, a characteristic pattern of peaks and troughs between 4.2 and 5.2 microns in wavelength. This was not an instrumental artifact. Artifacts do not produce molecular signatures. This was not disk dust, either dust scatters starlight. It does not produce molecular absorption lines at precise wavelengths. Whatever NIRSpec was seeing had an atmosphere, and atmospheres are the exclusive domain of planets. But further verification was needed. Could this rich atmospheric source be a passing brown dwarf? A background object? A distant star with an unusual chromosphere? The IFU mode had something more to offer. It measures not only the chemical composition of a source, but its motion, the Doppler shift of the spectral lines, which reveals the radial velocity of the object, whether it is moving toward or away from us. By extracting this information, the team measured the object's speed. Its position, its speed, its alignment with the disk plane, everything was consistent with an object orbiting Beta Pictoris. Not a background star. Not a wandering brown dwarf. A planet. Ruffiot summed it up with an economy of words that says everything. By obtaining a spectrum at the same time as the image, we were able to quickly confirm our suspicions. Follow-up observations with a second James Webb instrument, MIRI, the mid-infrared instrument, covering even longer wavelengths, confirmed the presence of water vapor and methane in the object's atmosphere. 2 more molecules, 2 more atmospheric fingerprints. The identification was unambiguous. This was not an instrumental anomaly. It was a giant planet, adding an additional layer of robustness to the discovery. A completely independent team led by Ben Sutcliffe of University of Edinburgh and Marcus Bonce of the European Southern Observatory used ESO's Very Large Telescope and James Webb's NIRCam instrument simultaneously to confirm the existence of Beta Pictoris d. 2 teams, 2 approaches, 1 identical result. The planet is real. Gibbs, in NASA's press release, said a sentence that perfectly captures the irony of the situation. We weren't looking for a new planet. We were trying to understand one we already knew existed. Then this telltale signal appeared in the data where we didn't expect it. What Beta Pictoris d changes, the discovery of Beta Pictoris d is not simply adding a name to a catalog. It changes our understanding of a system we thought we knew and raises questions nobody had anticipated. Start with the system's architecture. Beta Pictoris now has 3 known giant planets. Beta Pictoris c, the closest to the star, at about 2.7 astronomical units. Beta Pictoris b, at 8 to 15 astronomical units. Beta Pictoris d, the farthest out, at roughly 30 astronomical units, Neptune's territory. 3 gas giants, all more massive than Jupiter, in a system only 23 million years old. This immediately raises a formation question. How could such a young system form 3 giant planets so quickly? In the standard model of planetary formation core accretion theory, a giant planet begins as a rocky core of roughly 10 Earth masses, which then captures surrounding gas to become a giant. That process takes millions of years. But the gas disk around a young star also disperses in millions of years. The time window for forming gas giants is narrow. Finding 3 gas giants in a system 23 million years old suggests their formation was triggered very early, perhaps earlier than standard models can easily predict. Some researchers propose the hypothesis of gravitational instability in the disk, a direct collapse of blocks of gas and dust into planets, bypassing the intermediate step of a rocky core. That scenario, faster than core accretion, could explain 3 giants in 23 million years. Beta Pictoris d, sitting at 30 AA distance at which core accretion models struggle to form a giant within the available time reinforces that hypothesis. Beta Pictoris D's atmospheric composition also provides valuable information. The presence of methane in the atmosphere is notable. Methane in a gas giant atmosphere is a temperature indicator. It survives only in relatively cool atmospheres. Its presence in Beta Pictoris D's atmosphere suggests that this planet, despite its young age, has already cooled sufficiently to maintain methane in equilibrium, which constrains its atmospheric temperature and, indirectly, its thermal history since formation. The carbon monoxide and water vapor complete a picture of a young gas giant atmosphere rich in carbon and oxygen. Beta Pictoris D is also, researchers say, likely responsible for a disk structure astronomers had been observing for years without being able to fully explain. The unusually sharp inner edge of the debris disk. Debris disks tend to spread gradually inward, where dust and debris can migrate. But Beta Pictoris's disk has a very abrupt inner edge, as if a force were holding it at bay. Models had predicted the existence of a planet in this region to account for that edge, a planet whose gravity would push debris outward and maintain the sharp boundary. Beta Pictoris D sits at exactly the right distance to play that role. The planet the models were calling for had been there all along. Nobody had seen it. One might object that 3 gas giants in a system 23 million years old might be the norm, that we simply lack the tools to verify other nearby young systems. Perhaps. But current planetary formation simulations struggle to systematically produce 3 giants in that time frame, except under particular initial conditions. Very high initial disk mass, early gravitational instabilities, or a combination of mechanisms still under debate. Beta Pictoris D is therefore also an observational test for those models. If it has the characteristics predicted by the gravitational instability scenario, a certain carbon fraction in its atmosphere, a certain molecular distribution as a function of altitude, future detailed atmospheric analyses will allow us to distinguish between the competing formation theories. There is also a statistic worth noting. Beta Pictoris is now only the second planetary system known to contain at least 3 directly imaged planets. The first is HER 8799, another nearby young star system with 4 directly imaged giant planets. These 2 systems, or 87999 and Beta Pictoris, are sketching the outlines of what might be a common type of planetary system. Young, richly populated with gas giants, still surrounded by a primordial disk. The natural question that follows is, how many other systems resemble Beta Pictoris, and how many planets are still hidden within them? The silent revolution Beta Pictoris D was not discovered the way you imagine a planet being discovered. Not a signal in a light curve. Not a bright point emerging from a core in a graph after weeks of image processing. A chemical signature? A molecular barcode appearing where nobody was looking, in data collected for an entirely different purpose. It is the first directly imaged planet in the sense that its spatial position could be discovered primarily through moderate resolution spectroscopy. Not through photons, but through molecules. Not through light, but through chemistry. The distinction is fundamental. Atmospheric spectroscopy has a property that direct imaging does not. It is nearly insensitive to the surrounding light background. No matter how brightly the debris disk glows in the infrared, it does not produce molecular absorption lines at precise wavelengths. When NIRSpec sees a co-barcode at 4.3 microns, that barcode can only come from a source with an atmosphere. The disk cannot mimic it. The technique effectively ignores the fog and retains only the signature of whatever has atmospheric chemistry. That is an extraordinary property. It means that planets hidden in bright disks, exactly the type of environment where direct imaging fails, can be detected through their atmosphere. And if they can be detected, they can be immediately characterized. You learn not only that they exist, but their temperature, their chemical composition, their velocity. Discovery and characterization are simultaneous. As Ruffio put it, a spectrum contains an incredible amount of information. You don't just learn that something is a planet. You immediately begin learning about its temperature, chemistry, and motion. Here is the question this technique now poses to all of exoplanet astronomy. How many planets are hiding in systems we believe we know, simply because direct imaging cannot see them? The honest answer is, we do not know. But Beta Pictoris D gives an indication of the scale of the problem. This system was observed for 40 years by the best instruments available at each era. Dozens of independent teams pointed their telescopes at it. Hundreds of scientific papers were written on its structure, composition, and planets. And despite all of that, a giant planet at least twice the mass of Jupiter, hundreds of times the mass of the Earth, was sitting there in Neptune's region undetected. Not because it was faint, not because it was small, because the technique used to search for it was blind to this type of signal in this type of environment. How many other Beta Pictoris Ds are hidden in systems we think we have fully mapped? How many giant planets orbit within bright disks around nearby young stars, invisible to coronagraphs, undetected by radial velocity because they are too far from their star? How many systems we believed had 2 planets actually have 3 or 4? The mapping of neighboring planetary systems we have conducted over the past 30 years with available techniques may not be a complete census. It may be a selective census exhaustive for a certain type of planet in a certain type of environment, blind to others. Beta Pictoris d opens the possibility that our picture of the architecture of neighboring planetary systems is incomplete in ways we are only beginning to measure. The power of the method extends beyond disk systems. Integral field spectroscopy, the approach used by NIRSpec's FU, can, in principle, be applied to any region of space, not only to young systems with bright disks. In any system close enough that James Webb has the necessary spatial resolution, you can analyze the light pixel by pixel and search for atmospheric signatures where no model predicts a planet. It is blind exploration, in the sense that it does not assume in advance what it will find. It simply looks at what is there. There is also a philosophical dimension to this discovery worth naming. Beta Pictoris is one of the most observed astronomical objects in history. It has served to train generations of astrophysicists. It is in the textbooks. It is in the lecture halls. It is in doctoral dissertations. Researchers have built entire careers around the study of this single system. And despite all of that, or perhaps precisely because of it, because we believe we knew it too well to keep searching a giant planet was hiding there, there is a principle in the epistemology of science that could be restated as, certainty is often a form of myopia. You see what you expect to see, with tools designed to find what they are designed to find. Changing the tool sometimes changes what exists. James Webb did not search for Beta Pictoris d. It was doing something else, studying a known planet, when an unknown planet revealed itself in the data. The instrument was not pointing in the right direction, and it still found something unexpected in the wrong one. That may be the most honest signature of an instrumental revolution. The great discoveries come not only from searching farther or more precisely in the same direction. They sometimes come from looking differently and finding in the data, in the place where there was nothing, something that had always been waiting to be seen. Gibbs's team now plans to analyze the available Webb data in greater detail to better characterize Beta Pictoris d's orbit, its precise temperature, and the full structure of its atmosphere. In a few years, additional observations will allow astronomers to directly measure the planet's orbital motion across the sky to watch it move, the way Beta Pictoris b has been watched moving since 2008, turning a chemical signature into a visual reality. Other nearby young planetary systems will be revisited with the same technique. The astronomy that followed Beta Pictoris for 40 years will now look everywhere else with new eye searching no longer only for distinct points of light, but for chemical barcodes in the places where the disks seem to offer nothing but noise. The revolution is silent because it overturns nothing immediately. It does not destroy 40 years of preceding observations. It places them in a larger context. It does not refute the decades of work that came before. It completes them, but in a way that fundamentally changes what we thought we knew. And the most enduring revolutions are often of this kind. Not a fracture, but an extension of sight that reveals that what we took to be the edge of the world was only the edge of what we could see until now.